Hello people. So last time we talked about binomial distribution. So you might remember it. It's the distribution you have when your random variable is the number of occurrences of one binary outcome in a series of experiments. And it's a discrete distribution. So you can have your variable equal to 1, equal to 2 or to 3, but you can't have something like 1.67 or something like that. So we have another prominent discrete distribution, and as you have already guessed, that's the Poisson distribution. It's named after French mathematician, physicist, and so on. So French scientist Poisson. Okay, so what kind of distribution is that? So again, just like in case of binomial distribution, events in Poisson distribution have to be independent of each other. So you have some random event which can happen in different moments of time, for example, and subsequent occurrences of that event should be independent of each other. Then your events should be separated. You can't have two events happening at the same time. And last but not least, the interval between your events, I should say mean interval between your events, should be the same. So I'll put it as constant mean interval. Or just constant interval. Just remember that we mean mean interval here. So if you have series of events which comply to these conditions, then number of occurrences of such event during a fixed time will have the Poisson distribution. So your random variable is number of occurrences again, just like in binomial distribution. However, there is a difference. So in binomial distribution, you take an event and you repeat it fixed number of times, and you count a number of occurrences of one outcome when you repeat the same event fixed number of times. So fixed quantity of events. Here, instead of doing that, you just wait for a set amount of time, and each time an event happens, you add 1 to your variable. So let's move to the examples to make it a bit more clear. So we have an example. It will not be a very good example. Well, in fact it will be a bad example, but just for now let's pretend that it's good enough. So you have your buses, public transportation buses, and let's say you are waiting at the bus stop. So more or less you have the same interval between different buses. Maybe it's 10 minutes, just for example. And you wait for an hour and you count how many buses passed you by. And well, if it was ideal, if they really came one each 10 minutes, you will have 6 buses in an hour. However, due to different random situations on the road, it won't be the exact 10-minute interval. So let's say you came to the bus stop at 1 p.m. and you caught one bus just at that time, so at 1 p.m. And the next bus came at 9 past 1. Maybe it moved a little bit faster than it should. Maybe it was very lucky with the stoplights and so on. The next bus got caught in the road jam, in a traffic jam, and it came late. So instead of 1:20, it came at 1:24. So it was not a very big road jam, maybe. And so on and so forth. And you can have something like, maybe something even like this, where some of them come way too early and some of them come way too late, and so on. So that's 48. And maybe next one is at 1:57, and so on. So if not for some details, that will be a Poisson distribution. You have 6 buses here in 1 hour, and maybe if you wait a bit more, you got your next bus at 8 past 2 p.m. And then it's at that time of the day when everybody leaves their workplace and goes for lunch, and some of them go home for lunch, and so on, and the streets are full and there are very many traffic jams and so on. So buses start struggling with their timing. So next bus comes not around 2:20 as it should, but at 2:29, for example, and the next one at 2:47, and the next one does not come until 3 p.m. So in your second hour you have only 3 buses, and so on and so forth, and you count the number of buses each hour, and those numbers, in ideal case, they would be distributed by Poisson distribution. However, as I already said, buses are not a very good example. So first of all, buses are not independent. So usually if the bus comes to the bus stop too late and there is too many people waiting for it, it will signal either the dispatch or the next bus. It will message them asking to come faster. So the next bus will come earlier than it should. So comings of the buses are not independent of each other. And we told that for Poisson distribution you should have independent events. Also, it's not impossible for 2 buses to come to the bus stop at the same time. That's also a no-no case for Poisson distribution. And that's why the buses are not a good example of Poisson distribution. In fact, they are absolutely not an example of Poisson distribution. However, they have that property of having approximately constant interval, and that's why I chose them. The better example would be, for example, rains or maybe storms. They have the constant average interval between two storms. Storms are independent and you can't have two storms at the same time. So if you have two storms at the same time at the same place, it's not two storms, it's just one big storm, right? So that will be the Poisson distribution. Well, now you probably noticed we have the ideal mean number during that time interval. So if buses come in ideal succession each 10 minutes, you have 6 buses each hour. And that mean number we will use Greek letter lambda for that number. And that's the only parameter of Poisson distribution. So let's look at what the probability will be. So probability of your variable being equal to some number k, and k is the integer number, will be, let me put it at the next line, so e to the minus lambda over k factorial times lambda to k, and that's your probability. So for our example with buses, lambda would be 6, and if you want to find the probability for one bus, you substitute 1 for k. If you want to calculate the probability for having 12 buses an hour, you substitute 12 for k, and so on. So that's the probability for Poisson distribution. Now, if you want to calculate the mean value for Poisson distribution, and I'm again using the Greek mu, the Greek letter mu, because that's the population mean, that's the ideal mean, it will just be equal to your lambda. And moreover, variance for Poisson distribution will also be equal to lambda. So that's the property of Poisson distribution. If you have a distribution with integer random variable and its mean and variance are equal to each other, then it's most probably the Poisson distribution. However, there is one more thing to Poisson distribution. So if you remember binomial distribution, your variable values for your variable are limited. So you can have, so let me put it here, binomial, you can have 0, you can have 1, you can have 2, and so on, all the way up to n. So for example, if you are tossing 10 coins, you cannot have more than 10 heads. You can have 11 heads because you have only 10 coins. For Poisson distribution, there is no such limitation. Your value can be 0, it can be 1, it can be 2, it can be 3, it can be 9, it can be 1,000, and so on. It can be any positive integer number, all the way to infinity. Just starting with some value, your probabilities will become too small. So for example, you will have something like 0.00000001 for your probability, or maybe even less, and so on. But still, it's unlimited. Binomial distribution, your values are limited. In Poisson distribution, they are not. So now, maybe we will look at some numeric example, and for that, I guess we will switch to, there is an application called Desmos. It's a very good graphing calculator, scientific calculator, statistics calculator. It's free, it's accessible on almost every platform, and there is also a web version and so on. So I will use that because using something like Excel spreadsheets on Android is too inconvenient. But okay, let's move to that. Be right back. Okay, so we are back, and here you can see the Desmos, and here I entered the function for the probability of Poisson distribution. I did not want to use all those Greek letters, so for mean, instead of writing lambda or mu, I just put m there. So e to the minus m over x factorial and m to the x. So that's our Poisson distribution, and here we have a table. I chose my mean to be 6, like in our example with buses, and I took the probabilities for 1 bus in an hour, 2 buses in an hour, and so on. And here are those probabilities. However, you might notice I multiplied by 100. I multiplied by 100 because I wanted my probabilities to be in percents. Instead of having something like 0.13, we will have 13%. So the numbers here are in percent, and here they are. I went all the way up to 17, and you can see the probability is already quite small. It's 0.01%, which is 1 in 10,000, which means that having 17 buses in an hour when the interval between them is 10 minutes is just, it's almost improbable. But if you wait for, say, 10,000 hours, then probably 1 time or 2 times you will see 17 buses an hour. Okay, so let's move here. That's our chart, that's our graph for probabilities. You can see, you might notice that the graph looks very much like the one for binomial distribution. The shape is close. We have that bell. In fact, we can turn it into a full curve. So let me put 6 here. Okay. I forgot to multiply by 100. Yeah, so that's our curve for Poisson distribution. Now, what happens if I change my mean value? So if instead of 6, I take maybe 10. So I will leave that curve intact. So the solid curve is for the case with mean equal to 6, and dots are for mean equal to 10 in this case. You might notice that the peak of our distribution shifted. It shifted to the left, and the height of that peak became smaller. So our curve has flattened. So if we change our mean value to be even larger, so maybe something like maybe 30, now it's very wide. Oh, by the way, that's the thing you get when you use negative numbers in Poisson distribution. Just don't pay any attention. Okay, so 30 is too much because here we don't have numbers all the way up to 30. But still, you can see where it leads. So if... oh, what am I even doing? Let's bring this back to 6, our dots, and instead we will change mean value here. So 10, and I will add another line with mean value equal to 20, again times 100, and then maybe something extremely large, maybe 100, and no, we don't need 20, buddy. Okay, let it be 50. I also will add one with smaller mean, so let's have a mean value of 1. And I'm consistently forgetting to multiply by 100. Okay, so you see, when you have larger values of mean, then your peak, the top of your bell, shifts to the right and becomes lower. And here is the one for 50. And you can see that it's much lower than the ones with smaller means. And when you make your mean value smaller, you have higher peaks to the left. And also, the peaks, the distributions with smaller mean are more focused, more concentrated. This peak here that we have for 1 is more narrow than this one that we have for 6, and the one that we have for 10 is more wide. So when you are increasing the mean value for Poisson distribution, your curve shifts to the right, becomes lower and wider. Even more low and wide, and here you can have extremely low and wide for 50. If I put something like 1000 in my formula for mean value, then that peak will be almost invisible because it will be too small. Let's try that, and I guess even 1000 is not even needed. Maybe 200 will be enough. Yeah, exactly. So here is our 200, and you can't even spot the curve. 50, the one for 50 is still visible here, even though it's very low. The one for 200 is almost on the line, and you have to zoom in way too much to be able to see it. And it looks like it's still invisible. Yeah, okay, so that's it. One more thing, you can use binomial distribution to approximate your Poisson distribution. So let's zoom back into a normal scale, and I will get rid of all those excess curves. So the one for 10, 1, 50, and 200. Now, we have the event that happens each 10 minutes on average. We can we can look at it like this. So let's divide those 10 minutes into, oh, what do you call it? Into smaller intervals, maybe 1 minute each. Yep, so we are dividing that by 10. And then I'll say that in each of those smaller 1 minute intervals, your event can happen or not. So we have kind of a binary event, and inside our interval we have 10 binary events, and that might remind you about the binomial distribution. So you can imagine this as tossing 10 coins and using binomial distribution for that. However, in case of fair coins, you have your probabilities being 50-50, so 0.5 and 0.5. Here it's not the case. So we have 6 buses in 10 minutes, and we have 10 smaller intervals in 10 minutes. Each of them is 1 minute. To find the probability of success for one of such smaller intervals, we take our mean number, which is 6, and we divide by the number of intervals, which is 10. So my probability will be 0.6, or 6 over 10. And now I will define an additional function for binomial distribution. So x and my probability, let me denote it by p for now, and number of trials is n, let's say. So we know the formula for that case. We have number of combinations, and number of combinations is just factorial of total number of trials. So n factorial over n minus, so here in our case it's x, number of successful trials, so n minus x factorial times x factorial. So number selected is x here in our case. And then we take our probability p to the power x, and then q, which is 1 minus p to the n minus x. So I just used the binomial formula here. You might refer our last class, the formula is there. However, instead of writing all that thing, n factorial over n minus m factorial and so on, we just put the number of combinations. So here I'm not sure if Desmos has inbuilt function for number of combinations, so I just wrote that in an, what do you call it? So I just put the formula here. Okay, so let's do it here. Again, I will multiply by 100 to have percentages. So our function is b, I called it b, x1. Now we divided our interval into 10. That means, so each of our smaller intervals is 1 minute, and during 1 hour you have 60 of such intervals. Now our probability of success is 0.6. Oh, okay, sorry. I should have put my probability first. Okay, 0.6, and then number of trials, which is 60. Okay, I multiplied it by 100, but I'm still kind of I suspect that it's not all. It looks, yeah, for some reason numbers are too small. Oh, okay, I see. So here, look, we have 6 buses each hour, not each 10 minutes. So you have 1 bus each 10 minutes. And that means that you will have 0.1, 1 over 10 bus each minute. So instead of 0.6, I should have 0.1 here. Yeah, now it's good. And if we look at the graph, they are almost the same. Well, you still have your differences here at the maximum, but those differences are small. It's not even 1%. And if you make your n larger, then that difference will become much more small. So let's try. Let's go here in our table and let's change our n. So instead of a 60, let's take maybe 120. However, that means that this one, the probability of success will become smaller. Our n become larger 2 times, so 2 times larger than it was, and then probability of success becomes 2 times smaller than it was. And you can see that your dots are much close to each other. We can go further, so let's multiply this by 5. Let's have 600, and then we should divide this by 5. It's 0.01. Something went wrong. Okay, probably that's the problem with calculating factorial of 600, because it's a huge number in case of factorials. Yeah, but it's not even able to calculate it for 300, maybe 200s. What about 100? Yeah, for 100 it's okay. But we already looked at 120, right? So let me bring 120 back. And then I should bring this back. So just look at how close those dots are. And now I will change my n to 30. So I'll make n smaller. And 6 divided by 30 is 0.2. And now you can see that difference here is larger. So in fact I can plot the difference. 100. So my first function is, or maybe my second function, it doesn't matter which one I use. Nah, not a good idea. I'll have to adjust that manually each time. So just look at here, at the distance for these points, I mean this one and this one. And you did already see that for larger n, that's smaller. So that's it. We can approximate our Poisson distribution with binomial distribution. or we can approximate our binomial distribution with Poisson distribution. So you did already see that when you have large values for n, calculating the binomial distribution becomes problematic. So here when I substituted 300 for n, my software was not able to calculate it. And in such cases, instead of using binomial, you can use the appropriate Poisson distribution. So kind of go the opposite way around. And you can always find a good enough Poisson distribution for any binomial distribution, and you can always find good enough binomial distribution for any Poisson distribution. Okay, so for now that's all. Those are our main two discrete distributions, the binomial, which we tackled last time, and Poisson, which we did today. I highly recommend you to go through your textbook to refresh the topic and the best case, solve some problems, do some exercises. And that's all. Bye.